Okay, so welcome everybody. So tonight we're going to have a repeat on the RoPE, Rotary Position Embedding discussion. I think it's actually fairly lightweight, should go fairly quickly, although sometimes, more often than not, we say that and we still run over, but we'll give it a shot. So these are the papers that I went through when I was exploring RoPE. The foundational paper, it ties back into the attention is all you need, so transformers. And I'm going to do a quick, super quick kind of summary of the transformer and attention and what that is, and then how positional embedding plays a role in that. We'll go through, I've pulled out some graphics from a few different sources to cover that, the transformer stuff and the attention stuff. I pulled out some of the key equations from the RoFormer, which is the paper that introduced rotary position embedding. We'll go through that, and then I'll just, some of it will be repeat. We'll go through the paper itself, just kind of scroll through and look through that. And then Julius has got wanted to take the mic for a little bit and talk a little bit about, would you call it warp rope or something like that?
Yeah, warp rope.
Yeah, we'll do that. And then if we have enough time and if there's interest, I had gone through, I was wanting to kind of get a feel for how this stuff works. And so I coded up some of the math and ran some examples and played with, what's it look like when you rotate attention and rotate keys and all that stuff. So we can play around with that. So that's kind of the agenda. Again, and then this position interpolation. We're not really going to have enough time for that, but these two are kind of things that position interpolation is one of the things that's kind of enabled by the rotary position. That's kind of interesting. Maybe skim through that. And linear attention is referenced within the RoFormer document. I don't think we'll really get into it very much, but I did provide the link to that anyhow. Okay, I also watched a few videos on RoPE, and this is the list. It kind of goes from lighter to more detailed. The Deep Learning Hero went into it fairly, I think that's a 40-minute video or something like that, starting with efficient NLP was a 10-minute-ish type of paper, or video rather. So if you're interested in kind of following up, I should take this document, let's see, Google Docs. Let me post this into the chat in case anybody wants to follow along on that. There were some additional resources. One of them, the first couple of ones, I think is where I went and grabbed some of the images, graphics for the slide deck. And then this last one was kind of a nice blog on rotary embeddings that I thought was a useful read. So with that, okay, so quick background on transformers then. So this is the kind of the top image, the first image out of the Attention is All You Need document. We've been through this a number of times, but it shows the original architecture with both encoder and decoder. Most of the models that we look at these days now are decoder only, so they're only the right-hand side. It shows the embedding. So this is the token embedding, and then how positional encoding. In this case, it shows plus because the position embedding for the original document was actually additive. So you took the embedding of the token and you actually added in the positional, the embedding for the position. And then that was fed into the multi-headed. Okay, so let me see if I can do that.
You can just go to that share, yeah. Right, so if you say read to people with link.
Okay, hopefully that gets you where you need to be.
Thanks, Roger.
So, yeah, so you add in the embedding and then you run it through the various weight matrices to generate the key value and query vectors, and then run that through multiple layers through the MLP feed forward, MLP, et cetera, up the stack. So this is the part that's interesting. This is the part we're going to play with today is this positional encoding. How that comes to play. So the idea here is here's your inputs, goes through the embedding for the tokens, positional encoding gets added. So the graphics of that is this is representing the embeddings 0, 1, 2, 3 for the tokens. I don't know what you call the token. Is it the X, the numerical representation, or the text? But nevertheless, there's an embedding for each of those tokens, and you actually add in, literally add a vector of the same dimension, and that gives you the embedding plus position vector is what this graphic calls it, the EP. And this EP is something that's just computed in the original document. They use these equations, sines and cosines, where they have the position, the current position in the stream. So I think it'd be 0, 1, 2, 3 is the position. And then 10,000 to the power of 2i, so the dimension. So what they're going to do is they'll do pairs of these. So there'll be a bunch of sines and cosines. And then essentially, if you think of this as kind of the theta, the frequency at each pair changes by a factor, I think, of 2, right? As you go up to the whatever you'd call it, the higher index number dimensions. And that ratio is this 2i over the dimensions. So I goes up to d model, from 0 to d model. Anyhow, so this was it's certainly what was used by the transformer at that time. I think it was kind of standard practice. Actually, I'm not sure where that came from, but anyhow, that's the embedding, position embedding that they used in the original transformer. Any questions or additions, clarifications on that so far? Whoops.
So maybe two things that I would add, Roger.
Yeah.
Right. So one is for every position, you will get a unique set of values from those sine and cosine formulas.
Mm-hmm.
Okay. And the way I think of it, which is probably not necessarily exactly right because they're sines and cosines, right? But like you could imagine that if one of the sines has a very high frequency, it's repeating over and over and over and over and over again. Okay. Let's say it repeats every, I don't know what, every, 10 tokens or whatever, right? Then basically it's telling you the value of your position mod 10.
Yeah.
It's telling you the units digit, right?
Yeah.
And if you have something else that's repeating every 100, it's a longer way, slower frequency. It's repeating every 100 tokens. Then it's telling you, well, it's giving you mod 100, which theoretically you can read both the tens and the units digit, right? But the units digit might be kind of low precision. It might be a little hard to read. So if you combine those two, then you can get a very quick, accurate read of both the hundreds digit and the tens digit, right? And so, by doing this, right, theoretically, if you say, I'm really interested in a token that's exactly, 134 positions away, there is a formula that you and I can concoct that says like, yeah, based on reading out the thousands digits, the tens digits, the units digit, we can find something that's exactly 134 away. The other comment I would make is that because this is a high dimensional space, like a 512 dimensional space or whatever, like you could imagine that perhaps you're adding these positional embeddings and you're kind of confusing things because you're moving your token embeddings. But it's also possible that maybe these position embeddings are sort of occupying a certain number of dimensions out of the 512, and your tokens are occupying a different subset of the 512, and the two of them maybe don't really overlap, and so they're not really interfering with each other.
Yeah. Yeah,
And you
this is
can't
where
really
it gets
show
that.
that in a,
This is where that part where I still don't feel like I have a good intuition about high dimensional space. But yeah, you're right. I mean, you're adding these position embeddings, which seems like you're shifting your vector, but in reality, the original information is still there as well. Um, even though you've
yeah,
shifted,
yeah.
you're
And
still close to
if
what it
they're
was
in,
before it shifted.
right, and if they're in sort of orthogonal subspaces, right? Um, so so if you were able to find the right way to sort of rotate that 512 dimensional vector, you might actually find that with the right rotation, then some of these embeddings look sort of like zeros in most of the values. Uh, and vice versa, you might find that your token embeddings look like they have close to zero values in some of the dimensions,
Mm-hmm.
and that the two of them are sort of, occupying disjoint dimensions.
I will, with that, to follow your comments, two things that went ahead here is, this is a quote out of the original Attention is All You Need paper. So this is where they were using these embeddings that I've just described, same thing. Um, and they said right down here, we chose this function because we hypothesized it would allow the model to easily learn to attend by relative positions, since for any fixed offset k, position embedding of pos plus k can be represented as a linear function of e pos. So they they kind of understood early on that relative positioning was going to be important. They tried to anticipate that with this position embedding. And it's, I guess I haven't worked through this math on in my head, but apparently it is a little more difficult to learn this type of relative positioning as opposed to RoPE that we'll see later on that learn better. The other one was one of the things I had done was kind of code it up. So this was just coding up that equation for the sine, cosine, and I was just plotting the sine. But if to kind of emphasize, what does this look like? What do these dimensions look like? I'm plotting like from position 0 to 100, from 1,000 to 1,100, and 10,000 to 10,100. So that's horizontally what these three represent. And then looking at out of the 512 dimensions, the first dimension is this one, as you said, is a very high frequency type of thing. And it doesn't change much from the beginning to the end, except if you look closely, you can see there's a phase difference here. Like these aren't all coming in at exactly the same time on where the windows start. As you go up higher in the dimension, so here's dimension 50 out of 512, you can see it's lower frequency, again with the phase shift between at the different points. And it keeps on going as you go higher. Interesting when you start getting up into these dimensions. I'm at a token position 10,000, and it's well, I guess it shifted from 0.1 to 1, almost 1. So it's funny, that looks at this scale, that doesn't look, that looks like the same slope. It seems like it should be different slope, but anyhow, that shows kind of the multiple the higher frequencies, the middle frequencies, and the lower frequencies, and shows how they phase shift as you go through the time sequence from position 0 out to position 10,000. It also to me says it doesn't, out at, if I take 250, I think I'm just still going on the first cycle. So it seems like it embeds a pretty long sequence doing that. Any questions, or did that help with anybody to understand what Ted was talking about, the different frequencies?
Hey Roger, do you have this image that I put in the chat, or some version of this?
No. What is this?
I've seen this many times.
Let's see, I'm not
So
am I sharing this right now? Probably not, right?
if you're sharing your entire desktop, then
Yeah,
if you
I
click
wasn't.
on it, it may or may not, I don't know. You could paste it onto an empty slide.
So what does depth mean? The depth axis?
Yeah, so I've seen this so many times and I have a general intuition, but I don't know exactly what it is. So I think the way this one is drawn, okay, um, the token position starts on the top and it works down. So it goes 0 to 50. Okay. And then the left to right represents the different positions in your embedding vector. So the far left is the first float, the 0th float, and then the first and the second, whatever. And so
The
I
coordinates
suppose
of
It's more like
the
depth is
coordinates of the
equal to
embedding.
dimension.
So the depth along the vector, basically.
yeah. So if you're trying to compare different tokens, then when you look on the far left, you see that the value changes very rapidly, right? That's the high frequency one. So maybe that's the one that repeats every 10 positions or whatever. And so it's akin to like a modulo 10 function or whatever, you know. And then the one next to it, I don't think it's quite going to be 100, maybe it's every 20 or whatever. But clearly you can see on the far left, they change much more frequently. And then as you get to around the 20 range, you can see they sort of change more slowly. And then by the time you get to 60, they're really slow, and then they don't seem to change at all to the right of it. Maybe you'd need to look at positions beyond 50, you know, look at 100, 200 or whatever. But so this is a visual representation where the color represents the value of a given thing.
Mhm.
And it's gonna go blue, white, red, white, blue, you know, just like a sign or whatever. But it's just a more visual representation of what you have.
And in the
Kinda
right
like if
half, in the right half where we have alternating 1 and 0, it looks like, is that really happening, or is this just a
I think it,
Yeah.
you know, because of taking small steps, you basically have different phase shifts on similar, very long wavelengths. And so that's why you just sort of see this. Oh, no. Because it alternates between sines and cosines. And so
yeah, I
sines
thought
start at
Okay.
0 and cosines start at 1. And
Oh,
so,
okay.
yeah, like if you look,
actually, it might be easier if you just took all the even numbered ones, all the sines,
Right.
and put them in one image,
Right.
and all the cosines in another image. Maybe
Right.
that would have been a better way to show it.
yeah, I think if you look at the formula, you got two of them. One for 2i and one for 2i plus
Right.
2i plus 1. If you look at some previous slides, I think that's what it's about. Like
Yeah, but
odds and evens have different.
yeah, I didn't
Um,
make this. I think the intuition would be easier if you put all the sines next to each other and all the cosines next to each other
Yeah.
as two separate images.
Right.
Then you would have a solid blue one for the cosine on the right, and the solid white one for the sine on the
Right.
right. Yeah.
Right. And so for the sign on the right, the white signs, it's basically saying these are all such small angles theta, they've hardly moved off of 0 yet. You can't even tell the shade difference. But if you went far enough, eventually they would start to turn blue as they got to like pi over 2, right? And then the cosine similarly would go down from dark blue towards white as they eventually got to pi over 2.
It's interesting how it modulates the lower dimensions, but not the higher dimensions of the vector. That's, you know, it's like it just kind of degenerates in the upper dimensions. You're not getting a lot of,
Yeah.
you know.
And kind of this is my point, that if you don't really care about tokens that are very far apart, right? You can see that these higher dimensions are essentially constants.
Right.
Yeah.
Yeah.
And so,
Mhm.
you know, you're free to use that space for token information, and you're not really losing much, whatever.
For positional encoding.
Yeah. But so what, as you keep going, Roger, then we'll talk about what's the difference between. So what I'm saying is, yes, you and I can come up with a formula to figure out the relative, like a distance of 20. So we'll get the same value if we're comparing 20 to 40 as comparing 40 to 60. Okay.
Mm-hmm.
What's going to come up in your slides, I assume, Roger, is okay, so you and I can come up with a formula, but is it easy for a transformer to calculate that formula? It
Right.
might be doable, but it might be very complicated. It may take it multiple steps. What you want is something that for the transformer, it can calculate super quickly in one layer. You don't want it to be something that requires 4 layers just to figure out your 20 tokens apart.
Right. Right. Thanks for sharing that. That's a good high density visualization of that.
Yeah.
Okay, I think we finished this then. So this is using the additive and position embedding. So once we get these embedding plus positions up here, these guys, the transformer then takes those values at the first level of the transformer. So we're talking about down here. Notice that the position encoding is only added at the first level. This block is repeated multiple times, and between the blocks, you don't have the position encoding. So it's just at the very beginning when they come in. So this is this one's representing just that very bottom layer, actually before the input to the bottom layer. But once you have those position embeddings of the tokens, then it multiplies those by 3 weight matrices, the WQ, WK, WV, to get query keys and values for those specific positions. And then those guys, I think this is trying to represent that they're multi-headed attentions. So there's 3 of those that'll generate 3 different query vectors, 3 key vectors, 3 value vectors. For each one of those, you take the query, do the dot product with the key. That gives you kind of a similarity number coefficient. You multiply that by the value, and then you sum up all of those, and that's the output of that layer. Ted's got another one here. That's a nice one, Ted. Yeah, so that separated the two, didn't it? Sine and cosine. Anyhow, so that is the mechanism. So the aggregation here. So we use a softmax on those then to generate the output values. The softmax is used to do the weighting. I don't know where the softmax would have been represented. Should have been represented as a layer kind of in between here. Your alphas are the outputs of those, the softmax layer, I think. Okay, we did this already. All right, so as we said, the relative positioning was something that they had envisioned from the beginning was going to be important, and found that it wasn't performing as well. They were looking to improve that. One of the ones, this is in the T5 model apparently, they use a relative positioning model, but instead of, what they do essentially is have a bias that they add. And if you look at kind of along this diagonal, there's the B0. So there's a bias that says self-attention on the current token. And then there's biases that say, one to the left, well, I guess it wouldn't be one. Now, that's interesting. This one shows it. Does anybody know, is the T5 a non-causal? Is it not? I thought it was
it's
a
actually encoder decoder, so it does have a decoder on the output side. That's
so this could be on the encoder side then, yeah, for the T5. The disadvantage of this apparently is that, so each time that you shift a token, basically you need to add the embedding, position embedding back to the token embedding, because it's shifted. For this token, the bias that you add is 0 initially, then -1, then -2, -3, -4, etc. So every time that you go and calculate this, you have to recalculate what was called up here the EP, the embedded position, so the token with its position embedding. You have to recalculate that every time. And so that apparently is an overhead, and so this slide represents that performance drops off when they use the T5 bias. It doesn't perform as well as these other embedding mechanisms, position embedding mechanisms. This one, I looked at it real quick. I forget what the alibi was another position embedding that in here looks really good. But there was some, I forget what it was, but that one I don't think is caught on like the Rotary. Does anybody know? Ted, do you know alibi?
I've heard of alibi. Maybe we do it next week.
Could be. Yep. There's a couple topics that could come up for that. Yeah. But anyhow, tonight's rotational. So that's kind of the background of what's the problem we're solving and what a current approach is. What I want to do is I went through and grabbed a few of the key equations out of the paper. We'll go through those first, and then we'll kind of go through the paper in whole, and we'll revisit some of these, but add in a little bit more. So they do kind of a analysis, and they compare it to existing position embedding techniques. So they start with a formula to describe the position embedding. So this is a formula that will generate, or a function that's going to generate the query keys and values of a token given its position. And in the case of absolute embedding, we're taking this PI, which is what we saw earlier, that the sinusoid equation, this one. They're taking that and just adding it to the embedding, and then you multiply the matrix, the weight matrix, by the times that to get your query keys and values. So that's the absolute positioning as we've seen before. There's been different approaches for relative positioning. So in this model, the keys and values are being computed by adding a relative position. So this would be an example of the T5 bias. So you would be adding a relative bias to the token. And I think there were some of those, were also, they tried it doing learned ones. Was that, Julius, was that one of the ones in the original Attention is All You Need? They looked at trying to learn those positions also, right? And found that these learned positions actually were similar performance, I think, to the sinusoidal positions.
That's my memory, yeah, that
Yeah.
they tried it. They tried learning the positional encoding, and it didn't perform significantly better.
Yeah.
Yeah, so I think the learned ones would be the top formula, the absolute embedding.
Yeah, that's what I was, yeah. So the relative ones, did they, I guess maybe the only example on the relative is the bias that I saw, the T5 bias. There might have been other ones, other approaches as well. Okay, so what this paper proposes is a different approach. What they're going to do is still use the same weight matrices for the query and key, but they're going to use this rotation. So it's a complex. So I is square root of -1. M is the position of the query, and this theta is really back to, I don't know if in the abstract approach that they said this, but it ends up being the same type of number that they have in here, where you're scaling different dimensions at different speeds. And so each of the tokens is rotated then by position relative to the position, and then the attention between the two, between position M and N, is going to be this the real component of this. So it's the difference, the angular difference between the two. So the weight matrices don't have rotation in, it's just based on the position, in this case, the position difference between the two. one of the slides, videos had a picture like this that represents it. So if you have an embedding dog that's at this location, if it's the beginning of the sentence, it would be at this location. If it is token number 2, it gets rotated by some amount theta. And if it's in position 5, it gets rotated by more. So this is the idea that it's just representing in 2D. So it, what we're talking about really is rotation in this very high dimensional space, but this represents what it looks like in 2D, is that you're rotating based on the position. And that gives you both an absolute position, but it also gives you a relative position, because any two words that are similar distance between them will have an angle that's the same, regardless of where they are in the sequence, token sequence. Any questions on that? Does that kind of make sense?
So I don't know if this is too early for me to jump in here, but the thing that I haven't really thought through is, obviously this is 2-dimensional and you need a much higher dimensional space, okay? But
Right.
What if the word tree is where the rotated dog is, right? That's clearly a bad thing.
Right.
If basically tree at position 1 is the exact same vector as dog at position 2.
Right.
So you kind of want to make sure you're rotating things into sort of an unused part of your vector space, is my guess.
Yeah, that
And you
makes
can do that.
Yeah, go ahead, Julius.
If you're willing to double the dimension, is that my echo?
No, I don't know.
Let's see. I'm turning on.
Yeah.
I'm gonna go into headphones. That'll fix it. Somebody's got an echo. But anyway, the doubling the space fixes it, because if you just think of it as introducing complex numbers, then that takes care of it, because all of your vectors are real. All your embedding vectors are real, and now you multiply them by e to the j delta, and so that's a whole new dimension. You've got a whole new, complex axis now, and so so you're guaranteed not to have any collisions ever, but you're doubling the space.
Is there anything that's okay? You're saying if you double the space, it guarantees there's no collision. But
If you wrote in,
except these are
what?
Oh, sorry. Some of these are cycling through, right? So you could rotate back into your space, original space.
If it goes too far, yeah.
Yeah.
But if it's e to the j delta, you can just, and if you have a context buffer of length L, capital L, then if you increment by 2 pi over capital L, then you won't ever collide. It'll.
No, that's
you'll
right.
have
Yeah, because your coordinates are going to be both a high frequency that does rotate it through the same space, but it will have a different higher dimension coordinate. So it's not really in the same original subspace.
Yeah, it can never collide, because you have a unique angle, and the whole angular dimension is reserved. It's like, it's like the cross product of your original space with a new imaginary axis.
Yeah, that's interesting.
Yeah, again, if you had one that rotated like 2 pi over 10 and one that's 2 pi over 100 and one that's 2 pi over 1,000, then you basically get your tens digits, your hundreds digits, your thousands digits, right? Just in terms of that frequency. Now, why I have a little harder time wrapping my head around it is they don't actually reserve half of their dimensionality just for the position embeddings. So then it's a little bit less clear what is being used. But conceptually, the simplest way to think of it is if you just assume that those are unused dimensions, and then there's no conflict between rotating and in this case, we're only using reals, but you can still imagine allocating half of your reals as if they were the imaginary components that went with the dimension right next to them.
Exactly.
So it's just, whatever cosine, x sub 1 plus I sine x sub 2. and then cosine x sub 3 plus I sine x sub 4, and so on and so forth.
And you're probably going to cover this from the paper. They actually take the coordinates and divide them in two, and they do a 2x2 rotation on all. You can think of it as pairing the coordinates and doing a rotation. So it's a rotation applied to that.
And we'll see they explicitly want them to have different frequencies that they repeat, so that you can read off different ones depending on what frequency you care about.
And maybe the if the embedding is learned, it may learn to kind of stay out of the way. You know, it might actually sort itself out.
That's what I was wondering. Usually these guys use like a pre-trained embedding, don't they? So that,
Yeah.
oh no?
Well,
Oh,
they
Token
start-
embeddings are usually learned.
or is
So
learned as
to
part of the
Julius's
model.
point, you could learn to stay out of the way of the rotation stuff.
Ah, okay, okay. Okay, I thought they were reusing the embedding, the token embeddings, but yeah, if you're learning that, then yeah, you can make sure they're, because it's a much higher dimension, so you can learn to stay out of the way.
So Ted, do they typically start with like word to vec and then learn from there?
I'm not 100% sure, but my understanding is it's just random initialization on everything.
Even the embedding, okay. It seems so valuable to have a really nice known embedding to just get started. You know, it's like an initial embedding and then let it kind of wander around from there.
But if you think about it, GPT-3 embeddings are actually way smarter than word-to-vec embeddings. So I don't think you gain that much.
So it just happens naturally in the first layer or two of the transformer. It just gets its embedding together, no problem.
Yep. Yeah.
Yeah, that's the other part I was thinking is that you could imagine that if you have a fixed token embedding, then the rest of it, the embeddings at the other layers could kind of learn to stay out of the way of those. Presumably the token embedding is going to have a lot of space, unused space left in it. So you could use.
I know people did do that with the absolute embeddings. Where you could say, I've predefined my token embeddings, and now I'll let those get learned.
Okay.
But I don't know if anybody ever studied to see like what is the rank of those, and are they actually like trying to stay out of the way?
Right. Okay. Okay. Good discussion. All right. Let's see. Anything else on here? This is just clarifying that, yeah, the attention model, then once you have your query key vector or value, you do a softmax on the dot product of the query and the key. And the scaling, so what did we read on this, Julius? Just today we read the scaling basically was
the square root of the model dimension, which is divided by the number of attention heads in the transformer. So it's really the attention head model dimension, which is like 1/8 of the original model dimension or something.
Right, because they were worried about the gradient of that exponential not being sufficiently large where they were interested. Yeah. So they did this division, which is interesting.
Giving it more dynamic range.
Right. Okay.
So Roger, do you have that other formula from the paper where they show that like if this rotation is an R, that once you do the query embedding transpose times the key embedding, that basically what you end up with is you have the two R's, and so then that's basically just R of n minus m.
I think you might be talking about this part where they're talking about these rotations matrices. Is that it?
Yeah. So the idea is, I think there may be another version of this, but yeah, if you look at equation 23, it's saying, hey, if I embed my query with this rotation stuff, then we're multiplying by e to the something on the right. And my key, I'm multiplying by e to the something on my right. But when you do Q transpose times K, then what ends up happening is since you're multiplying everything, then you get this product, and it ends up just being a rotation of n minus m.
Right. Down here.
And so that's the thing that they're saying.
Makes it
It's not only easy for the transformer to calculate this, but it's actually baked into the attention that we're already doing. So certain forms of, if you want to know the magnitude of this dot product, the transformer doesn't even have to invent a calculation to calculate positions. It's already
just
doing
comes
it.
out directly. So that's the easy to learn part.
Potentially. I haven't completely wrapped my head around it. Like, oh, so if you're 3 positions away, this thing's going to be a 0.5? Like, I don't know.
You can see that in equation 23. The last line shows you can see the n minus m factor there.
Yep.
So yeah, it's the e to the j delta. So it's just relative positional encoding, relative, query versus key.
Even
So
though
the relative distance is encoded in the RoPE.
It's clear the n minus m is encoded into that attention score. I'm just not sure that's the greatest thing.
Really?
Yeah, so like I'm trying to remember that what was the paper called? The indirect object identification paper, the IOI paper. Okay. So that's the one where they did things of the form. They had 2 names, and one was always male and one was always female. So it was like John and Mary did blah de blah. Then John gave the book to, and the indirect object that that the model has to complete is either him or her. And so they eventually were successful in identifying very specific pathways for how, I think it was GPT-2 small, how it calculated him or her. And there were some places when it was sort of keeping track of nouns and things like that, where it was using the word content or whatever. So so when you're referring, how do I say this? I can't like do the whole paper, but basically it's like John and Mary, blah, blah, blah. Then John, okay, so you see John a second time. How do you know John it's a second time? Okay, so one way you can know is you sort of look to see if I've seen the information content of this word before. And you're saying like this John is the same as that John or whatever. But there was this place in it where they showed that it was actually encoding like token number 1 or token number 5 was where I've seen this name before. And it was like an actual like number, where it was just saying like here is where. And so apparently these transformers do well because they've tested the rotary position embeddings, the RoPE embeddings, they work well. But with RoPE, I don't think you can as easily say like, given the embedding, I can just sort of extract from that, oh, this came from token position 5.
I thought my recollection was that they talked about this as having both absolute position information as well as easy relative position. So like your slide
It's
back.
what the authors said, but there is an absolute position for the word dog. But if you don't know what the word is, you cannot extract the absolute position from it.
I don't know. What do you mean if you don't know what the word is?
So when you looked at these embeddings, okay,
Uh-huh.
you don't even need to know what the word is in order to be able to extract these particular sine and cosine values out. The only issue is if the word conflicts with these values.
Yeah. Okay.
Okay, right? But when they were saying there's absolute position embedding, it's like, yeah, if you know the word is dog and
Oh,
you
I
know
see
the
what you're saying.
embedding is blah, then you know exactly which token position dog was in. But if you don't know if it was the word dog, then you
Gotcha.
cannot just simply say, looking at this embedding, I know it had to be the fourth token.
Okay. Because with this, where it's additive, it's actually part of the vector. You can, it's in there somehow.
Yeah.
Whereas
Yeah. So if dog
with
had
the rotation,
zeros in there,
yeah,
if dog had zeros in some of these values, then you would be able to just straight read these values out
yeah,
and say, oh, look,
yeah,
it was the third token position, right? Now, apparently that's not terribly useful because the transformers work really well when they don't have this. But that was one of the things that I was having trouble wrapping my head around is that they claim, they use the words, they say just exactly what you said, that there's absolute position information, but it's not absolute in the same sense. That's the point that I was trying to make.
Yeah, they actually they encode the position with is absolute, but the way it ends up in the token stream, or the embedding stream, is not extractable without the original token that was, or the original word embedding that was rotated. Yeah. I
Yeah,
can see that.
so you could imagine somehow when you're using rotary embeddings, the transformer is going to do different math. And so maybe somewhere it's going to keep track of the fact that the original word was dog, and now this is my current embedding. And so now you really are able to extract the absolute position by just saying what happens to my original dog, right? It's just a different calculation.
Yeah, yeah, yeah. Okay. Okay, so that's kind of a discussion around this point. Supposed absolute and relative, but mostly it sounds like we can utilize the relative more than the absolute. This was one, I don't know if Ted, if you had any insight into this decaying intertoken dependency with increasing relative distance. I think it appears a little bit later on in one of the graphs, but I wasn't exactly sure what that implication was.
Yeah, they even have that graph, and I don't know what that graph
Okay.
is. If you scroll down to
Yeah.
the thing that's sort of like an exponential decay, except it's got jaggies in it. I was like,
Right.
whoa, what is this? You have given me no explanation.
Yeah. And then linear self-attention with relative position encoding. I think that's kind of what we're talking about, that you embed it with these linear, like every token gets its coordinate, but then you have intertoken distances that are constant, depending on the relative distance between them.
Yeah, I don't know how important that is, but the linear attention was not doing dot product softmax. It's doing a different.
That's a that's a different place where they basically, I think that's different than what this is saying, but they
Yeah. So in that
okay, I see.
paper,
I see what you're saying. Yeah, yeah. So
in that paper, instead of softmax, they use a certain function.
Yeah,
We'll call it phi, which is an inner product in a higher dimensional space. But because it's an inner product, it preserves linearity.
right.
And so then what they're saying is if you know it preserves linearity, then you know how these multiplicative things are going to work, because multiplication like distributes nicely over linear
Yeah,
functions or
yeah.
whatever.
And with a huge
So
performance gain, right? They got it from order n squared to order n. That seemed like, when I first saw that, I was like, wow, this is exciting. But then I kind of looked around and it didn't seem like that has been as widely adopted. I wasn't quite
well,
sure.
it's fast. It just doesn't work well.
Yeah.
There's lots of other calculations I can come up with that are even
Fast.
faster, like always return all ones.
But didn't they in the
And
paper, I thought they showed it was relatively, maybe it's just not as good. It's not, it performs horribly, but
yeah, I'm being a little bit facetious, but I peeked at that Andrei Karpathy coding transformer from scratch video.
Uh-huh.
And so what how he worked his way up to attention is he said, like, hey, maybe we should just like do an average of all the tokens that have happened before. Okay. And then it's like, doing an average of all the tokens we've seen before, isn't that kind of simplistic? Isn't that kind of dumb? Like, maybe some of them are more important than others. Right.
And that's what RNN does. You could say an RNN just adds up all the tokens under an exponential fade. It's like an exponentially fading average.
Yes. So his was non-fading. It was just a regular average. But then he just showed that, like, hey, if I just hard code my attention scores to be all ones, I've recreated my average.
Okay.
Because they all just get one, and then you sum them on the bottom and you put yours on the top, and voila, this is basically just your average. So my point is that, yeah, if instead of using softmax, you just used this like average of all tokens function, like Karpathy did, it's much faster. It just doesn't work very well. But his point was, it actually does work better than just a naive bigram model. It is an actual improvement. So he coded a bigram model where he just said, based on this token, I'm going to predict the next token based on nothing but this is, so what's your prediction of the next word? The dog. Based on dog, what's your prediction of the next word? Right? The dog ran.
Okay.
Based on ran, what's your prediction of the next word? And then he said, instead of just using the one word, I can average all the words that came before it. So it was kind of a neat progression, and he showed that it actually does better than a bigram model. But instead of having even weights on all of them, let's actually have uneven weights based on what it is. Then the question is, can you learn good relative importances of all the previous words? So that's sort of a hand wave at that point, right? We none of us know how it learns.
Did he cover the linear transformer?
No, he didn't. But I'm saying that that's another example of a much faster calculation.
It doesn't work as well.
Which works even worse than linear attention. It works like crap because you're just
right.
But so I'm being a little bit facetious, but it's kind of to prove a point. Many papers have proposed things that are faster. If they would work as well, it would be the aha moment. And so far, nothing faster that has any of those kind of sort of linear-ish properties. None of them have actually worked as well as the non-linear.
I was a little confused why that was even included in here. Why they had to bring in the linear attention, but
when was this paper?
Yeah, that's what I was thinking. It might have been that was exciting at the time.
Yeah. I think in 2021, attention was still new enough, and linear attention and those other ones, performer, reformer, blah 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 blah, were still exciting. It's when you got bigger than GPT-2. Right? When you get really big, that's when these weaker, faster transformers, but weaker transformers, when they sort of plateau out. And they don't get any better. But then GPT-3 using full softmax nonlinear just got even better performance. And so it is something where you do need a certain size to be able to tell that this thing has maxed out its representational capacity.
Okay, well, let me, I'm going to have to pick up the pace a little here.
Sorry.
No, that's okay. We're doing some of this out of order, but okay, so what were we doing? So this is background work, just going through characterizing the base functions or the base equations they're going to work with. So a query at position M is going to be some function of the token at M plus the position M, and K and V the same way. And then attention becomes this dot product and softmax, and then you weight all the values by that. So I think we've seen that before. We've already covered this expression of absolute position embedding, and relative position embedding. I'm going to skip through this stuff, and then their proposed approach. They do it kind of abstractly to start with. They say we want functions that look like this, and then kind of say that, you know, in 2D that this rotation matrix satisfies those requirements. We've already looked at this equation. Expressing this with real numbers, you can, in 2 dimensions, can use it with the sine and cosine representation. And what they say is that once we've solved it in 2D, let's just go ahead and for dimension D equals some even number, we'll just represent as this block diagonal. And then, so it's the rotation times the weight vector times the position embedding, or excuse me, not position embedding, the token embedding.
Hey, Roger.
Yeah.
At the risk of beating a dead horse, so that equation up above where they had that G and whatever, what they're really saying is they wanted an embedding that had an invariance where, say, the word dog and cat are 3 words apart. The attention score will be identical, whether it's the 1st and 4th word, or the 10th and 13th word, or the 100th and 103rd word. That no matter where you were, absolutely, if they're 3 apart, the attention score will always be the exact same value.
Right. Okay.
That's what this equation 11,
equation 11 is. Yeah. Yeah.
Is expressing this invariance that as long as you're 3 apart, as long as you're 5 apart, you'll always have the same score. How useful that is remained to be tested on actual, like, building one, training it, whatever. But that's the invariance that
okay. And then 12 is there. Here's one realization of it in 2D. And
my understanding is that this is what people are using now, that, you know, the old original sinusoidal modulation of the coordinates is out and RoPE is in. In all the papers I've read recently, that's what they use for positional embedding. So it must do pretty well.
Yeah. And sinusoidal went out very fast. People just allowed the model to learn its own. And then when you look at it, you would see actually sinusoidal patterns in the embeddings, but they were not hard-coded, handcrafted sinusoidals anymore.
I didn't know that. So the original sine cosine that was proposed in attention is all you need. So that kind of lost favor pretty quickly, didn't it?
I mean, basically, I think the original attention language translator is the only model that ever used those embeddings. And then after that, everyone just let them train their own. Maybe not only, but like all the famous models, you know, had their own, like say GPT had its own learned embeddings.
Yeah, there's quite a bit of research on that. And I guess whatever's more recent is whatever stood the test of time.
Yeah. Okay, let's see, anything.
For what it's worth, I do not understand figure 1.
Yeah,
I think they're trying to communicate something, but I don't think the colors mean anything. And so for a long time, I was trying to figure out what the colors mean.
Yeah, Julius and I were doing the same thing, and it's like, okay, I get the equations better than I get this visual. Yeah.
Yeah. I think the color is supposed to say, oh, look, there's some additional information in this box,
Added
which
into
is the
it,
rotation. But it's not literally telling you. I don't know. I can't even figure out where the query and the key are and whatever.
I guess this is all the dimensions and you're adding in a rotation on each dimension, I guess, is what the colors are different on each pair, are they? Or the color across?
Yeah. I guess in the middle where it says position 1, 2, 3, 4, 5, 6, that's the color. The color of the number is the color of the little
that gets
added at the bottom. Yeah. But it is, in my opinion, a little misleading because there is not necessarily a free lunch where you can add that little colored stripe at the bottom without losing any of the other information that you had.
Yeah, assuming that what you had filled all the dimensions. Yeah. But we kind of don't.
Right.
We kind of assume there's room there.
So like if they colored the whole box a mix like the top one, a mix of gray and red, and then the next one, a mix of gray and whatever that color is, olive drab, and then a mix of gray and green, right? That would, to me, be a little bit more, because it's like, yeah, you're blending it together and it's not clear. You can extract all the original pieces from
Yeah.
that blend.
Yeah.
So,
Yeah.
sorry.
No,
beating
that's
a dead
okay.
horse.
Okay, here's, I just noticed actually this is where they make the comment about the long-term decay property. And I think, Ted, you alluded to this graph, right? Yeah, long-term decay of RoPE. Whereas you get further away, if two tokens, one's been rotated by 100 positions, then it's what, half the magnitude of the dot product of one that hasn't been rotated, a relative rotation. My
I really
guess,
don't know what this diagram is.
I ended up with something similar to this when I did it, played with it. My guess is that some of these other signals that you're getting on top of this are, it's those higher frequency rotations that are, you're getting closer, you're getting further, you're getting closer, you're getting further. And so they're adding some modulation to that.
So what is
The
plotted?
weird
What is
thing
the
is-
y-axis?
Oh, maybe this has to do with their formula had some 50 or whatever hard coded into it. Because I was like, how come there's really no squiggles between 0 and 35 or whatever? You know what I mean? There's almost no
Yeah.
squiggles. And then the squiggles seem to kick in around 50.
Yeah.
But
In the
It looks
beginning,
like another
maybe
product.
everything's moving in the same direction. Like all the signs are moving in the same direction initially. And then you get some that are catching up, cycling past, and others that are continuing to draw apart.
Yeah.
But I think this is, yeah, the long-term decay aspect. Basically, the idea is that, and I did a little bit of this here where I coded up the algorithms, and you could see where.
Yeah, like you could just do dog crossed with itself. So that's the maximum.
That's
possible.
one, right? That's one, right?
And then you just have them be farther and farther apart.
Yeah, and that's what I did. I took like a key and query that matched 100%. And if you don't add position embedding, then the dot product is 1. If you add a 0 rotation, so they're both at the same position, and you rotate it, then it's still 1 because they're both, they've been rotated the same amount. Actually, not rotated. If you rotate one of them, in this case, I rotated the query, then you start to get a change. And if you rotate it 10 positions, it's decayed down. And then if you have two of them that are both rotated 10, it's back up to 1 type of thing. So that's, if we plot that, I think we would get that curve.
Okay.
that
Yeah.
we're seeing in
So you can see that after whatever on that curve in the paper, after a certain point, 100 or whatever, it's like small. But then after about whatever 200-ish, it's kind of seems to have reached its, but then it's still on
It's
their
still
chart
down.
squiggling between 6 and 10 or something
Yeah.
like that.
Yeah.
So I feel like they're making a pretty weak statement. Like, broadly speaking, things over 100 are lower than things less than 100, but it squiggles a lot. Like that. What kind of statement is that?
Yeah.
And what is their angular step? Or what is their maximum sequence length? I guess that would be equivalent.
Oh,
Yeah, I think I was going to
example.
ask that.
Like yours is 512 or something?
Well, I think they use 10,000, assuming that your
Yeah.
sequence length is going to be less than either 10,000 or 5,000 or whatever.
Yeah, I was going to ask that because it seemed like that's what it was saying, that after 10,000, it kind of like the relative distance kind of repeats. And I know these days everyone says, oh, we got the longest content length. It's in the millions or whatever. So I was going to ask about that.
Yeah, I'd like to know. I don't know the answer to that one too. I would also like to know, like, what are the techniques they're using to get these? There's actually, I'll inject it right now just because we're talking about that. Let's see, which one is it here? This was a really interesting paper, extending the context window of large language models via position interpolation. What they were doing is they were using rotational embedding like this, but when they wanted to extend the window, they essentially interpolated the points in between, but don't go more cycles of the position embedding, but just scale it to be more points, more positions. And they resampled this sine wave at a higher frequency. This is real similar to what we saw with Mamba, where they had those, what do we say, Lagrangian polynomials, that they could change the context window by resampling these continuous functions. In this case, resampling the sine waves. I thought this was really interesting paper because it talks about training it on a particular window size and then interpolating it to be a longer context. So you never trained it on 4,000, but you were able to do this interpolation to extend the context window out to 4,000.
I need to take another look at that paper. I'm familiar with the general concept that they interpolated, but it seems to me that if the original model learned how to find words that are 2 words apart, then suddenly it would be finding words 4 words apart.
I think there was a, see if I scroll down real quick. I think there was a very short fine tuning. So,
Oh,
I don't want to get distracted on it, but
yeah,
if
sorry.
I remember, they did a 1,000 cycles to do fine tuning on the new embedding. So it was an easy thing to learn, I guess, because the functioners are continuous and you've already been in that space.
No, but that makes sense that they had to do something that they couldn't just as is interpolate and voila.
Yeah, because all the weights, all the queries would have been set for a particular scale. They need to change that. Yeah. Let's see, anything else? The one other one was this, that matrix. So conceptually, you can think of these rotational matrix as looking like this, which apparently Julius got really excited when he saw that rotational matrix. But that same thing.
It says it all.
Yeah. Conceptually, you can think of it as this rotation matrix, but when you implement it, you can translate that into an element-wise product of the input vectors and the cosines with these different scales, and then I guess kind of reordered elements and some signs in there. And that is the same thing with a fraction.
I think in this form you can see the source of that long decay, because you can see that if you have a small relative distance, then your cosine isn't moving very fast and the inner product will be large. But if you go a large distance, then you'll be wiggling much. So it's basically like the Fourier transform of a sinusoid, how it tails off. So another way to just say it is that it's more correlated at close distances, and then at far distances, the correlation decays because of this modulation, really.
Interesting. So we should actually be able to just plot this, the magnitude of this thing, over time, and see the long-term decay that you're talking about.
Yeah, as you increase m, if you plot m on the x-axis, and just plot the magnitude of the dot product.
Yeah. See that? Yep. Okay. Julius, did you want to jump in with here's the last part I'll say is that, so what they're showing is that the performance, these guys, as they train them, they seem to learn faster. And I think is probably the key thing that made them popular. It's not a dramatic difference, and it's not a dramatic improvement, but it's a small cost, and you get there faster, type of thing.
Mm-hmm.
Okay.
The plot that launched 1,000 PyTorch implementations.
All right. Why don't Julius, did you want to share?
Okay, so yeah, I'll give my little quick update. Let's see, Zoom, share. Okay. Oh, disabled. I'm still I'm locked out.
Okay. Why?
So
Yeah.
summarize.
So that'll be on your security menu, Roger. You can
This new
check
one, it does,
the,
it has, I don't see this the same way. Share screen, okay. Try that.
Yes, it's working.
Okay.
Let's see. Should just say share. Hopefully you can see my presentation.
Yep.
Do you see? Okay. So let's see if I can go back one. Let's see. Let's do it like. So this is what I talked about last time. Just to kind of recap that, if you think of rope like this as just a delta by a fixed angle, and 2 pi over L is a good choice if you know your maximum context buffer is length L, then that all makes sense. But if it's indefinitely long, like some sort of RNN situation, then the idea, which is directly inspired by bilinear transforms in signal processing, this is something we apply to the frequency axis to map the infinite analog frequency axis, the J omega axis in the S plane, to the unit circle in the Z plane. So it's a finite. So you have to map the whole spectrum of a continuous time signal down to a finite spectrum. So it's just borrowing on that idea, and coming up with a scheme for just warping it. And so we talked about that a little bit. And so I added a couple of things. So here it is again. The problem with it, the main problem with it I see is that it's more expensive because it doesn't want to be autoregressive or recursive, because as you move forward through time, you can shrink the delta for now, but you can't change long ago delta. So whatever you started out with, that's what you've got. And so in a recursive formulation, it's compressive going into the future. And the only place I can think of where that makes sense would be something like encoding a journal article into a vector for a RAG system or something like that. Think of the journalistic style where all the good stuff is at the beginning. They have a really cogent summary of everything, and then they go into a little bit more detail. And by the time you get to the end of the article, you're just getting really detailed interviews with people and so on. That's not as critical. So it's an interesting compression of the timeline toward the end, and that can be done recursively, then throw it in the database. And of course, you can also just, flip things around, and offline is no problem. And for transformers, it's no problem. But I don't know. I just, I feel like it's not an interesting recursive thing. And it also, it sounds like rope when you say it. So I think that's another reason to let it go. So thinking about this more, I thought, well, what it really suggests is that you go ahead and just have a finite sliding window. And if you're going to do that, you might as well use the TIIR trick that we talked about just briefly. So that's the truncated infinite impulse response technique. And this is also just straight out of well-known signal processing. And so I thought about that a little bit. And so here's where TIIR filters come up. So you've got this sliding window, and so instead of just doing a brute force sliding window, you have this recursive formulation. You can think of it as this identity. The sum of z to the minus n over capital N samples can be formulated like this, and this can be broken down like this. So this is a digital integrator. And then you subtract the same digital integrator at the end of your buffer link. So it's basically just canceling the tail of an infinite window. So that's the basic idea. So what you can now do is take two RNNs and difference them and get a non-fading linearly roped memory of any length L. And you get to decide what L is. You can decide dynamically what it should be. So this is to me what I would rather work on rather than, W rope. I would like to, check into this. So here's the way the state would update. So you have your usual state update, the hidden state, and then you subtract off the old one, and that gives you, you know, just the input if it's just one sample difference. And here we have here you have it written out, and so this is the subtraction of the history. And so and there's a problem with floating point round off error only if you're decaying, only if you're not in complete precision. But if you're in fixed point and if you don't have a fade decay, then it can be exact. So that doesn't have to be a problem. And this is my finale. So this is just the same state space model we had before. And it's got a state expansion factor here. I have a nice new notation for that. So Z inverse underbar was to vectorize a scalar to the model dimension. And if you have two underbars, that also includes the state expansion factor. So it's a vectorization of a vectorization. And I like this double underbar notation. So double bar Z inverse is the state expanded delay. So it's, you know, if it's size, well, here it is length L. So if your sequence length is L, then it's L model dimensions long in terms of total numbers, but there's no computation here, right? This is just a circular buffer, and you just need the storage. There's no actual computation. So your input comes in, it gets multiplied by your input gating matrix, and here's the skip connection, and it's just one because we know better. It would normally have a D here for the D matrix in a standard state space model. And so you go into the summer that adds to the hidden state, and then you can linearly rope it, you know, just rotate it by e to the j2 pi over, and you know that's right because you're going to enforce it, right? And so then you go into an L sample delay line at the model dimension, and then you come back and subtract. And so this is what subtracts off your, you know, rectangularly windowed memory. And because, and if everything's in fixed point, and if it is, you know, full precision adders, which is easy, right? You just need a few extra guard bits, then you're going to have perfect computations, and there's no accumulating round off error like you normally get. So if these were floating point and you had round off error anywhere in this loop, then this subtraction would not be perfect, and you would not exactly cancel the tail. And that would be a problem. And there's a fix for that, which we can talk about sometime. It's the standard TIIR trick. But this is, I think, really cool. And what I want to play with is, you know, trying it out. I want to compare this to Mamba because it's sort of in the Mamba family. But it's just, this would normally be a gain here. This is the feedback matrix A, and it's diagonal nowadays. And in Mamba 2, it's a constant diagonal matrix. And so that would be something like 0.999 something, and it's learned as e to the minus, you know, delta, where delta is a learned parameter. So that's the that's what I would go put up against Mamba to try to see if I can get some better results. And by the way, since you have all this stuff here, since you have an L sample delay line of your inputs, you can go ahead and do an attention sum. You can, you know, do some query value key stuff and bring out an attention sum if you really want it. So you know, you're sort of upward compatible with a length L transformer coming out here, and it could add into the skip connection. You could add it into the RNN memory. This is your output gating for the RNN, which is in Mamba and all the modern RNNs. You know, gating is on input, gating is on output. So that's it. And so this looks really promising to me. And the only thing it doesn't have is, you know, a full A matrix. And as I was mentioning to Roger, there's this new paper out showing that without an input dependent feedback matrix, you're not able to do permutations and long-term tracking of objects. And so that's another thing we could talk about. I actually have that also in my, where is that thing? It's called The Illusion of State and State Space Models. So check this out. But the answer is, you know, you need a full matrix. So it's much more complicated, much more expensive. And I don't know if anyone wants to spin that, but this is really a slick, fast little thing. I'm going to program it up in PyTorch and give it a spin and see what I can come up with, see what happens. I think that's
So
all
you do have a kind of a waterfall. Anything that falls off the end, you can't access in this model, right? The tail is gone, so you can't access.
It's gone.
Yeah.
Yeah, it's like a transformer in that sense.
Yeah.
It's absolutely finite.
Well, the transformer doesn't well, I guess it does. Yeah. Once you hit
Yeah, so
your context window.
But it's much cheaper.
Yeah. Yeah.
It's it doesn't have the quadratic problem, right?
right. So
It doesn't
it's
have
much
quadratic
cheaper, but if you were reading a really long paper, maybe a paper that's longer than it should be, and if they introduce some concept at the beginning and you're more than L tokens later, now you're screwed because you
That's right.
like Roger was saying, you absolutely cannot reference that.
Yeah.
And,
Yeah,
and
so
in
this is
fact,
limited to
with your
applications.
fixed point math, there's not even any hope. You're saying you have guaranteed 100% that you've deleted any influence that the L+1 token could have ever had on you.
Yeah, it's completely subtracted away. Unless you add some new thing, to save it in some long-term memory that's not decaying.
Right.
But yeah, this part of it is truly a finite, and that's the idea. It's a truncated infinite impulse response implementation of a finite impulse response. So this has a finite memory implemented using an infinite memory. This loop is infinite, but its tail is being subtracted off exactly.
Right.
That's cool. Maybe you could compare it to like a regular RNN and see if it can beat it for moderate sized Ls.
Yeah, and it also gives you the control. So you have a full vivid memory for length L, and then if you want a little bit fuzzier memory for things beyond that, you can always throw it into an RNN that just behaves like RNNs do. So at the output of this, this delay line could feed into a Mamba, for example, that will then decay at whatever rate it wants, and it will give you an infinite tail, but a fuzzier infinite tail.
That's kind of my intuition. It feels like having different categories of quote unquote memory, and also something where as the tokens are coming in, you can make a decision about kind of what type of memory does this belong in.
Yeah.
The small words, the and whatnot can just be thrown away. Somebody's name you want to hang on to for a while. Don't put your hand on the stove. You keep that for a very long time. It feels like somehow those things, as they're coming in, you're able to make an assessment of, is this likely to be something I need later
Like
on?
a hippocampus.
Yeah.
And the hippocampus layer.
Right.
It's like if we have mixture of experts, why not a mixture of memories, and let the hippocampus unit decide,
Yeah.
when to route to long-term memory.
Yep.
Mm-hmm.
And then you can, yep.
But
And
if
you
I
can
could
have your
make
sleep
an
time.
analogy, it's like my teenage kids don't know that the advice that I'm giving them should go in the really long-term memory, and they're putting it in the throw it away immediately bucket.
That's right. They have a rapid forgetting factor for anything except video game, cheats and such.
No, but like that is the dilemma, right? Is that nobody's come up with a model that can figure out which are the long things and which are the short things. And the only solution so far has been attention keeps everything. And therefore
And more.
you don't have the problem of accidentally throwing away something that later on you realized, oh my gosh. You do have the problem of how do you decide amongst all of the things that you've kept around what to use? But it seems like we've gotten pretty strong at solving that problem. Not perfect, right? But pretty good at, like, I've got 64,000 things and I can still pick the one I want.
It seems to me though, Ted, in the beginning, I get it. It's hard to decide what to keep and what to throw away. But if you have kind of a curricular approach to it, where in the beginning you're learning that and you're learning the likelihood, you always want to remember a little bit more than you think you're going to need, but you're starting to learn more and more what are the important things to remember, and that allows you to get a longer and longer context over time. It would require that multiple cycles to be able to train it that way. But I don't know, it just feels like there's something missing there.
Yeah, I
We
mean,
were,
there's hope. There's hope that Mambo or something will actually get that algorithm close enough,
yeah.
you know?
Mhm.
But that's the rub.
Another thing that I think is interesting is like if you're doing a specific application, like let's say sentence embeddings, and that's it, that's all you're doing, then at the end of a sentence, you can clear this thing very easily, right? It's very simple to, you know, you can change L dynamically, and you can clear it manually with just an extra coefficient here that just goes to 0. So I'm interested in manual control of the memory based on known situations.
Yeah. All right, well, should we call that a wrap? I had some code things that we could go through, but we're already after the hour.